everyone, today we're going to be looking at related rates. Related rates are a major application of differential calculus. Differential calculus is when we work with the derivatives of multiple different variables. You may be familiar with this from implicit differentiation, where we work with multiple derivatives algebraically. Related rate problems involve at least two changing quantities and ask you to figure out the rate at which one of them is changing given sufficient information about the others. Often these problems will use geometric formulas you are familiar with and ask you to differentiate the formula and solve for a variable such as the rate of change of the radius of a circle.
Now we'll show you an example problem to explain how this technique might be used. For example, the day after the Calc AP test, Ms. Proksch decides to take the entire class on a field trip to the Golden Gate Bridge to study the parabolic nature of the cables. When Jack leans over the edge of the railing, Ms. Proksch accidentally steps backwards without seeing him and knocks him over the edge. When Jack hits the water, he causes a circular wave to spread out at a rate of 3 meters per second. At what speed is the area of the circle growing when its radius is 5 meters wide? Let's write down what we know. The radius of the circle is 5 meters, and r is changing with respect to time at a rate of 3 meters per second. We know that at any given time, the relationship between the radius of the circle and its area is a equals pi r squared. Our goal is to determine the rate at which the area of the circle is changing with respect to time. So we can take the derivative of both sides of the equation, getting dA dt equals 2 pi r dr dt. As you can see right there. The power rule gives us this answer. Now we can plug dr dt and r into our equation to determine the answer.
Here's another example which will involve another geometric formula you're familiar with. Jack somehow survived Ms. Proksch's assassination attempt and wishes to get even. When she climbs a 10-foot ladder to change a light bulb, Jack gets an idea. As you can see, the ladder conveniently forms a right triangle with the wall. Jack pushes the base of the ladder so that it slides at a rate of 6 feet per second, and the area of the right triangle changes at a rate of 15 feet per second. The top of the ladder remains flush against the wall as it slides down. How fast is the top moving when Jack has pushed the base of the ladder so that it is 6 meters away from the wall? Again, let's write down what we know. Let's call the distance between the base of the ladder and the wall x. We know that right now x equals 6 feet. The rate at which x is changing with respect to time is 6 feet per second. The rate at which the area of the triangle is changing with respect to time is 15 feet per second. Since it is a 10-foot ladder, we know that this side of the ladder, or the hypotenuse of the right triangle, is equal to y equals 10 feet. We can call the distance between the top of the ladder and the floor h. So what we're trying to do is find dh dt, or the rate that h changes with respect to time given all the above information. Clearly, we need to relate the quantities x and h. We can do so using the Pythagorean theorem, as they are both sides of a right triangle. X squared plus h squared equals 10 squared, or 100. What we care about is the rate at which these quantities are changing with respect to time. We can find these out by taking the derivative of both sides of this equation. Deriving x squared and h squared simply yields 2x dx dt and 2h dh dt respectively. And since the length of the ladder is not changing, it stays at 10 feet long, the derivative of 100 is of course 0. So 2x dx dt plus 2h dh dt equals to 0. To calculate dh dt from this equation, we need the three variables x, dx dt, and h. We know that x equals 6, dx dt equals 6. Now we need to find h. We can isolate this using the Pythagorean theorem equation. 100 minus x squared equals 100 minus 36 equals 64. If 64 equals h squared, therefore h must be equal to 8. Now we can plug all these values into the equation 2x dx dt plus 2h dh dt equals 0 to find dh dt. After simplifying, we can see that 72 plus 16 dh dt equals 0, which we can rearrange into 72 equals negative 16 dh dt. Now we can solve for dh dt and see that dh dt equals to negative 4.5 feet per second.
Unfortunately for Jack, Ms. Proksch was not so easily defeated. She makes Jack wear a conical dunce cap as punishment and forces him to teach the remainder of the lesson on related rates. To demonstrate an example problem, Jack takes off his dunce cap and pours water into it from a water bottle at a rate of 4 liters per second. The circular top of the dunce cap has a radius of 6 inches and a height of 24 inches. When the water in the cap is at a height of 3 inches
At what rate is its height changing? Let's write out what we know. The water is pouring into the dunce cap at a rate of 4 liters per second. That conveniently is the rate of change of the volume of the water in the cap, dV dt. We also know that the radius of the cone is 6 inches and the height of the cone is 24 inches. We are asked to find the rate the height is changing when the water is at 3 inches. Let's write out the equation of the volume of a cone. V equals 1/3 pi r squared h. If you try to differentiate this formula using the product rule or holding high, it gets too complicated for us to be able to solve for one variable. Instead, we use a trick to remove one of the variables. Since we want to solve for h, we'll set up a second equation to find r in terms of h and substitute it in. We do this by setting up a problem with the cone. If you imagine half of a cross-section of the cone, you get a right triangle. We will draw two similar right triangles. The first one uses the dimensions of the cone, radius 6 and height 24, and the second one, referring to the dimensions of the water, is described as simply r over h. Warning! It may be tempting to plug in the height the problem gave us at this point, but that will give you the wrong answer. At this point in the problem, we are dealing only with the relationships between variables, and we cannot plug in numbers until after we've differentiated the equation. We solve the proportion for r because we want to substitute away all variables besides h. By cross-multiplying that, we get r equals 1/4 h. Now we can substitute 1/4 h into our original equation for the volume of the cone, so that we get v equals 1/2 pi 1/4 parentheses squared. Now we simplify the expression by squaring 1/4 h and multiplying it by the other h and 1/3. This gives us our equation of v equals 1/48 h cubed. Now we need to differentiate this equation because we're trying to find dh dt. Using the power rule, we get dv dt equals 3/48 pi h squared dh dt. The fraction 3/48 simplifies out into 1/16 pi h squared dh dt. Now we plug in the value for dv dt, which as you recall is 4 liters per second. And the value for h, which is the height of the water, is 3 inches. So now we have 4 equals 1/16 pi 3 squared dh dt. And we're trying to solve for dh dt. The 3 squared gives us 9. So now we have 4 equals 9/16 pi dh dt. We can now isolate dh dt by dividing 4 by 9/16 pi, and the answer is dh dt equals 64/9 pi. Thank you very much for watching this video, and we hope you learned a lot about related rates, and also that Miss Proksch is not one to be messed with.